So good morning to all. I am Sakthi Prabha, Assistant Professor, Department of ECE, Satyabama Institute of Science and Technology, Deemed to be University, Chennai. So this session we'll see about the subject Digital Logic Circuits, Unit 2, which is Design of Combinational Circuits. And in this session, we'll cover some of the very important topics, that is how to design and how to implement a half adder, full adder, and half subtractor and full subtractor, and also how to design a parallel binary adder and parallel binary subtractor. And also we'll try to solve some problems which is related to decoders, encoders, and how to design a multiplexer and demultiplexer. So let's get into the session. So introduction to combinational circuits. So basically, a circuit is said to be combinational where the output depends only upon the present input value. Okay, so always for a combinational circuit, the output value depends only on the present input value. So when you look into this block diagram, you can able to find here. So this is the block diagram of a combinational logic circuit where the output of this logic circuit depends only upon the present input value. So what input value you feed as an input to the concerned logic circuit, based upon the input value, the process will be carried out and you will be getting an output, right? So here in this combinational circuit, we are not giving any other sorts of inputs like feedback input or something like that, right? So once if you give an input value, based upon the input value, a process will be carried out and immediately you will be getting an output. So such kind of circuits, we call it to be combinational circuit. So in this case of combinational circuits, we never make use of any memory units, because memory units is not needed to store some of the input data or some other feedback input data, right? So the combinational circuit always comes with absence of memory unit, and also we never make use of any clock pulse. So clock pulse is also not necessary for designing a combinational logic circuit. So some of the combinational logic circuits are like adders, half adder, half subtractor, full adder, full subtractor, decoders, encoders, multiplexers, demultiplexers, and so on. So all these are considered to be a very, very good example for combinational circuit, which means all these circuits, your encoder, decoder, multiplexer, demultiplexer, everything, the output of these circuits, okay, depends only upon the present input value which is fed by the user. Okay, so now let's see how to design and implement a half adder circuit. Okay, so basically this half adder circuit, okay, it is a kind of circuit which is used for performing binary addition. You can able to perform binary addition over here, but here it is restricted to maximum number of 2 binary bits. Okay, you can able to add maximum number of 2 binary bits by using this half adder circuit. Okay, so let's see what are the steps which is being followed for designing and implementing a half adder. So the very first one is the block diagram of half adder. So before getting inside the implementation part, first you want to know how many number of inputs are there and how many number of outputs are there in a half adder. So as I told you, a half adder circuit, it is mainly used for adding maximum number of 2 binary bits. Okay, so those 2 binary input bits, I'm naming it as input A and input B. Clear? So now, what about the output for a half adder will be generally when you perform an addition, your output will be a sum as well as a carry, right? So output for a half adder circuit will be a sum as well as a carry, right? So this is the block diagram for a half adder. So once you design a block diagram, automatically you can able to conclude that how many number of input lines you are going to use and how many number of output lines you are going to use. Okay, so once the count value of line, okay, so your second step will be designing a truth table for this half adder. So how you design a truth table? Basically, truth table can be designed by the combination of input and output. If you know clearly the input value and the output value, you can able to design a truth table. So truth table always it consists of input and output, where the input, how many inputs are there? Yes, maximum of 2 input lines. So input A and input B. What about your output? Output is sum and carry. So sum and carry. Okay, so I have represented it over inside the truth table. So now, since we have 2 inputs, that is input A and input B. So number of input used here is 2. So n is equal to 2. So as per the formula, 2 to the power of n, which is 2 to the power of 2, which is 4. So for 2 inputs, we will be getting 4 combinations of binary bits. So 4 combination in the sense, our input combinations will be 0, 0, 0, 1, 1, 0 and 1, 1. So this combination has been arised based upon how many number of input value you give inside your circuit. Okay. So once the combination has been determined, now you want to calculate the output, that is for sum and carry. So here binary, normal binary addition performed. So when you perform a normal binary addition, so tell me how come you'll be getting the output, the sum and the carry? Yes, 0 plus 0, normal binary addition, your sum will be 0, your carry will be 0. What about 0 plus 1? Your sum will be 1, your carry will be 0. What about 1 plus 0? Your sum will be 1, your carry will be 0. And what about the last combination 1 plus 1? Yes, when you add 1 plus 1, your sum will be 0 and your carry will be 1. How come you are getting it? So normally you just take an example. You perform a normal decimal addition. You perform a normal decimal addition. How come you will be performing a normal decimal addition? 1 plus 1, which is nothing but 2. So 2 you divide it by the base of the binary. What is the base of the binary? It is 2, which we saw in the previous class. The base or the radix for all binary number system is 2. So when you divide the 2 with respect to 2, automatically what will be your answer? Is 1, 2 is 2. So 1 hyphen 0. So 0 you will be carrying it as a sum. Okay, so 0 you will be representing it as a sum, and that 1 which is being defined you will be carrying it as a carry. Okay, you will be representing it as a carry. So this is how you perform normally a binary addition. You perform repeated division. Okay, so now in terms of truth table, you have done the binary addition. So you got the output value for both sum and carry. So that is our second step has been completed. So in step 3, once the output value is being obtained, now we want to design what? A K map, right? So you want to design a K map. So K map, we have plenty of options like 2 variable K map, 3 variable K map, 4 variable K map, and so on. So now we want to choose which variable K map must be used for this truth table designing. Okay, so now how many number of inputs are here in the truth table? We have 2 variable inputs, 2 inputs A and B. So automatically you can able to choose a 2 variable K map. So always a K map will be chosen based upon the number of inputs available in the truth table, or based upon the number of inputs available in the circuit. Okay, so since we have 2 inputs, based upon the 2 inputs, you are going to design a K map with 2 variables. Okay, so 2 variable K map. So how you will plot the values initially for sum and for carry? For sum, you want to check how many number of ones are available. So based upon the number of ones available, you want to check the combination for A and B. So first look into the sum. So for sum, how will you plot the variable, or how will you plot the values in the K map? Yes, 2 times you are getting the number 1, right? So sum 1 has been obtained when A equal to 0 and B equal to 1. And for the second time, sum 1 has been obtained when A equal to 1 and B equal to 0. The rest 0, you will be neglecting it. You won't consider. So when A equal to 0 and B equal to 1 for sum, okay, for sum, when A equal to 0 and B equal to 1, I have obtained value as 1. So I have plotted over here. Same way in the second combination, when A equal to 1 and B equal to 0. When A equal to 1 and B equal to 0, I have obtained 1. So I'm plotting it over here. The rest are 0. So just I'm negotiating it. Okay. So now after plotting, what will be my next step? I want to group it, right? So grouping. So maximum number of cells available in a 2 variable K map is how many cells are available? 1, 2, 3, 4. So 4 variable, when 4 cells are available. So based upon that, you can able to perform the grouping. So 4 cells in the sense maximum number of grouping is quad. So as I told you in the previous online class, always you have to perform the grouping right from the maximum number of cells. So first you have to go for octet, then quad, then pair, and then only isolated grouping. So here maximum number of cells available is 4. So grouping possible. The first grouping possibility is quad. So quad is not possible, because quad in the sense here in first cell also you want to get 1, and over here also you want to get 1. Only then you can able to perform quad. So here quad is not possible. Then come for the next level. What is our next level? Pair. Pair in the sense 2 cells can be grouped together. So how come you can able to perform that grouping? Check over here whether 2 cells can be paired together. No, because the numbers, the cells are, the values are present in the diagonal model, right? So you don't have any other option. So the last final option is nothing but the isolated pairing. Isolated pairing in the sense single group of cells. Okay. So once you make a single grouping over here, that is isolated pairing, what will be your final expression? over here it is A bar and over here is B. So my sum will be equal to A bar and B. And what will be my the next value over here? This is A and this is B bar. So A B bar. So my switching expression or my Boolean expression will be A B bar plus A bar B. So A B bar plus A bar B is nothing but what? A XOR B, right? So you can able to finally reduce this expression by using the formula A XOR B, which is A B bar plus A bar B. Same way, same procedure can be carried out for carry also. So in carry, how many number of ones are available? Only a single time you are getting number of ones. And what are the combination? 1 and 1. So when A equal to 1 and when B equal to 1, you are obtaining 1. Remaining everything is 0. So grouping is possible for isolated type, right? So isolated grouping is possible. So what will be my answer along X side? Yes, it is A and over Y side it is B. So my carry is equal to A, B. Clear? So by or with the help of, with the graphical representation of the schema, I can able to define or I found out the Boolean or the switching expression for both sum as well as the carry. Okay. So now what will be my final step is, based upon this Boolean expression, I want to design a logic diagram for half adder. I want to implement, okay, or I want to design a half adder circuit. So how I am going to design a half adder circuit? So it has been designed based upon the Boolean expression. So now let me start with sum is equal to A XOR B expression. So A XOR B in the sense input here is A and input is B. Okay, so two inputs A and B are XOR together. So XOR in the sense you will be making use of an XOR gate. Okay, so I'm taking A as an input line and B as another input line. When I feed these two input lines inside an XOR gate, what will be my sum? My sum output will be equal to A XOR B. Okay, so now what about the carry? Carry is equal to AB, which is A dot B. So A dot B means you are performing multiplication. So multiplication can be achieved by using an AND gate, right? So from A, I am taking one line over here, and from B, I am taking another line, and I am feeding it as an input to an AND gate. So what will be my carry? Carry is equal to A into B, which is your Boolean expression. So this is how you design a half adder circuit based upon the Boolean expression which has been available or which has been obtained from the schema. Clear? So this is how you start designing and implementing a half adder. So totally we follow 5 steps. So what are the 5 steps? Very first step is you want to define how many number of input variables are there and how many number of output variables are there. For that we design a block diagram. So once the number of input and number of output variables are being defined, what will be our second step? Immediately you can design a truth table, because truth table is a combination of your input and output. If you know your input variable and if you know your output variable, only then you can able to design a truth table. Okay, so you know 2 input and 2 output. Based upon that you are designing the truth table input output AB with sum and carry. So once the second step has been completed after performing the normal binary addition, what is our third step? The output obtained in your truth table, you are going to design a K-map. So you want to design a K-map. So K-map will be plotted first initially based upon the number of ones available in sum and number of ones available in carry. You will plot the value in the K-map. After plotting the value, what will be the next step? You want to group. Once grouping has been done from maximum number to minimum number, after that, what will be your next expression? So the Boolean expression is very lengthy. You want to apply basic Boolean laws or basic Boolean algebra. Thereby, you want to reduce the lengthier expression. Lengthier expression, you want to make it into minimum. Okay, and thereby, once the reduced expression, you want to design a logic diagram for the Boolean expression. That will be your fifth or the last step. Okay, so this is how you start designing a half adder with the 5 steps. The same procedure is being carried out for half subtractor also. So half subtractor also you can able to perform subtraction for maximum of 2 binary bits. Okay, so there also you will be taking A and B. Instead of sum you will be getting difference, and instead of carry you will be getting. Okay, so instead of sum you will perform difference, you will be applying difference, and instead of carry you will be taking borrow. Same way you will be applying 2 variable K-map, you will be plotting the value, you will be grouping it, you will be finding out the switching expression, and based upon the switching expression, then finally you will be drawing the logic diagram. That is for same their binary subtraction. What is 0 minus 0? Minus 0 and what is 1 minus 1. So hope you are clear about how to design and implement half adder and half subtractor. So now let's get into the next topic, which is how to design and implement a full adder circuit. Okay, so for that also we follow the same 5 steps, but with a slight modification. So over here in full adder circuit, a maximum of 3 binary bits you can perform. Okay, that is maximum number of addition can be performed for 3 binary bits. Over in half adder, we performed addition maximum for 2 binary bits, but here you can able to perform addition for maximum number of 3 binary bits. That's the difference apart from the this is the block diagram and the truth table for the full adder. This is a diagram for a full adder. So full adder, as I told you, we'll be making use of 3 inputs. So A, B, and C, and output is quite common, sum and carry. So this is my truth table. Okay, this is my truth table. So truth table, how you will design your truth table? If your input number of input variable and number of output variable is known, automatically you can able to design a truth table. So input and output is being given over here, and we are listing all the input variable A, B, C, and listing all the output variable sum and the carry. Okay, so now over here in input, we have number of input n is equal to 3. What is the formula? 2 to the power n, which is equal to 2 to the power of 3, which is 8. So for 3 number of input variable, you will be getting 8 combinations. So 8 combination, which means starting from 0, 0, 0 till 1, 1. When you count, you'll be getting what? 8 combinations. For these 8 combinations of input binary data, you are going to calculate the sum and carry. So starting from 0, 0, 0, plus 1, sum 1, you are carrying 0. Same way you will be performing for all the steps until you reach your final 1 plus 1 plus 1. Okay, so now as a result of once you finish your truth table, you will be obtaining the value for sum and carry. So what will be your first? So you have obtained your output of your table. Based upon this sum and carry, you can be able to design what? Now we input variables are here. We have 3 input variables. Right? So what came up, you will be choosing the 3 variables came up, you will be choosing, right? Because the number of input here is, so 3 variable came up for sum, same way for 3 variable came up for carry. So once it has been chosen, I have to plot the value. So how will I plot the value? By finding out how many number of ones are available. So in sum, how many number of ones are available? 1, 2, 3, and 4. So 4 number of ones are available for the concerned combination. So for that combination, I want to plot the values in the 3 variable came up for both sum as well as 4. Okay, so for sum, 4 times I got the number. Okay, so 4 times I got the number as 1. To check for 0, 0, 1, I got the output as 1. So for 0, okay, for 0, 0, 1, I got the value as 1. So similar way, over for each value, I'll check the concerned combination and I'll be plotting the value. So once the value is plotted, what will be my next step? I want to, yes, group it. So for grouping, you want to find whether number of cells available is 8. So 8 is octet is possible. So whether all the numbers are filled value 1? No, it is not filled. So octet is not possible. Whether quad is possible, quad means maximum number of grouping is 4. So whether quad is possible, quad is also not possible. Pairing is also not possible. So only isolated grouping is possible. Isolated means single grouping. So single grouping, so 4 times the single grouping, so that you have to check over here. This is C and this is A bar B bar. So C, A bar, B bar. I'm rearranging it as per the order. So A bar, B bar, C. So as such, I want to perform, or I want to find out the concerned Boolean expression, and my final answer from sum, my final answer for the sum will be obtained as like this. Okay, the same way for carry. So for carry, how many number of ones are in? Yes, 4 number of here, 1 here, over here, and also last for final combination. So check for the concerned combination for A, B, and C. Plot the value. So once I plot the value over here, you can able to find, yes, grouping is possible, octet is not possible, quad is not possible, yes, pairing is possible. But here, when you look it over in grouping, over here I make 1 pair, and over here also I make 2nd pair, and over here also I make 3rd pair. So overlapping grouping is up to here. Okay, so 3 set of product terms I'll be getting over here in Boolean expression for here, right? Boolean expression is in mind. You want to check whether it is a very expression or it is lengthy. It's a length. So now you want to think that what are the Boolean rules of Boolean algebras you can apply for reducing it or simplifying the lengthier expression to a simpler form. So now I'm taking the Boolean expression sum value. Okay. So sum is equal to, I got it as A bar B bar C plus A bar B C plus A B bar C bar plus A B C, which is nothing but this sum expression I have written over here. So now here you want to check how come you can reduce this lengthier Boolean expression. So check the first product term with the second, last product term. When you check the first and last, you can able to find the term C. The variable C is common, right? So I'm taking C variable is common outside. So what will be my remaining product term? A bar, B bar, and over here AB. So I got it as A bar, B bar plus AB. What about the second and third product term? Yes, which is common here. C bar is common. So C bar, I'll take it outside. So what will be my remaining term? A bar B plus A B bar. I got this, right? So what is A bar B plus A B bar? It is A XOR B. So I can replace this equation as, this term as A XOR B, right? So A XOR B into C. Same way, the formula for that is AB plus A bar B bar can be written as A X NOR B. So over here, I'll get a circle also, dot circle, okay? So A X NOR B. So A X NOR B is nothing but the formula is AB plus A bar B bar into C. So this A X NOR B can also be further rewritten as A XOR B the whole bar. Okay. So thereby I'll get this concern expression. So when you look at this step, you can able to find that this expression, this A B bar plus A bar B, right? Is it looking as A B bar plus A B, which is nothing but A XOR B. What is my A? A is C. What is my B? A XOR B. So C X A XOR B will be my final or simplified expression, Boolean expression for sum. Clear? So this expression, draw the logic. Draw the logic. A XOR take input A B, give inside as input XOR gate, okay, and then I'll be getting an output. For that output, again I feed an input from B. Check it. So A as an input to my XOR gate. So one more thing. See, I have given as an input to the second XOR gate where I got the answer to be sum. Okay, so this is how I designed that. So sum for full letter. Okay. Expression and check whether so when you look into this entire expression, you can able to find how many variables are there. A, B, C, right? So key variables are there. So when you look to the last product, which variable is missing? So since the entire expression is of the form SOP, sum of products, I can write the missing literal or the missing variable as A plus B bar. Okay, so A plus so what will be my answer? So BC into A plus A bar, right? So just multiply A, BC into A plus BC into A bar, right? So I'm rearranging it as ABC plus A bar BC, and remaining term, second and third term, I'm writing it as it. So now when I look the first term and the second term, you can able to find AB as common term, right? So AB can be taken outside. So what will be my remaining variable? C plus 1, right? So you know, as per Boolean law, what is A plus 1? A plus 1 is 1. So same way, this is of the form A plus 1. So C plus 1 is 1. So AB into 1 is nothing but AB, right? So what is my remaining term? AC plus A bar BC. So I'm writing it as it. Now, so previously I found out what is the missing literal and I applied over to the last product term. So now in this step, I'm going to find in the second product term, okay, what is the missing literal, and I'm going to apply the missing literal over here. So what is the missing variable here? A and C is available, so B is missing. So I apply B over here. So what will be the final? So AC into B plus B bar. So same way you multiply AC into B and AC into B bar, you will get an expression. Over here, check which term is common. Over here, AB is common. So take the common term outside, and then you will get C plus 1. It is of the form A plus 1. So A plus 1 is equal to 1. So AB into 1 is 1 plus, and rewrite, you can write the same second and third term as such. Okay. So when you check the second and third term, again you can able to find C as considered to be common. Take the C outside. So what will be remaining? A B bar plus A bar B. So what is A B bar plus A bar B? It is nothing. So you got a reduced expression. For this reduced expression, now we are going to draw the logic diagram. Okay, so this is my reduced or simplified Boolean expression for carry. So what is my input? A and B. So B into so input line A, input line B, and going to give inside so A or B already you know you have obtained it previously, right? So this A XOR B, I'm taking the output over from here, and then I'm multiplying it with C. So C already we have a line over here. So from there I will take a line and I'm going to multiply, because this is of the form C into A XOR B. So multiplication. So it is being used. So I get the answer C into A XOR B. And what is my next product term? AB. That is A dot. So from A I take one line, and from B I'll take another line, I'll multiply it together. So my answer will be AB. So AB and C into XOR B will be OR together. OR means I'm performing addition. So for that I'm using OR gate. So my final carry Boolean expression will be AB plus C into A XOR B. So this is how you design a logic diagram for sum and carry. Okay. So follow 5 steps. Very first step is you want to know how many number of input variable, how many number of output variable are there. Based upon that, second step, you want to design the truth table. Once truth table is designed, third step, you want to draw the K-map. Okay. So K-map for the output variable, which has been generated in the truth table. Number is being plotted, grouped, and as a fourth step, find out the Boolean expression. If the Boolean expression is vacancy, try to minimize it in laws or basic Boolean algebras. Try to reduce it, make it simplified, and as a last step, final step, you have to draw the diagram for the uptime Boolean expression. Subtractor also. So full subtractor, yes, you take 3 in the ABC instead of sum and carry using different control. That's it. Okay. So here it's been said that you're designing a full adder with the help of designing. So previously in half adder, just I'll go to the previous slide to show you. Yes, in half adder, you can able to see that a half adder, it's nothing but a combination of a single XOR gate and single AND gate, right? So when you look into the full adder logic diagram, you look it over here. Yes. So single XOR gate and single AND gate is combinedly called as one half adder, right? Same way, another XOR gate and another AND gate is considered to be another half adder, right? So combination of two half adder gives you a single full adder. Okay. Yes. So same procedure is being followed for your full subtractor also. So hope you are clear about the concept behind how to design and implement a full adder and full subtractors. Okay. Now the next important topic is how to design and implement a 4-bit parallel adder and 4-bit subtractor circuit. So till now we were seeing in half adder we have seen we are performing addition for maximum 2 binary bits. In full adder we saw that it is mainly used for performing addition, binary addition for maximum for 3 binary number of bits. But over here in adder parallel subtractor, you have one of the major advantage that you can able to perform n number of binary addition, or you can able to perform n number of binary subtraction. It is not restricted to number of bits. Okay, it is not restricted to number of bits. That is one of the major advantage of parallel adder. So now let's see how you are designing and implementing this 4-bit parallel adder first. Okay, so adder in the circuits, yes, you perform addition. You perform addition for n number of bits for parallel adder. So here I have chosen, I want to design, the question given is I want to design a 4-bit parallel adder. Okay, so 4 bits, since it is a 4 parallel adder, 4 full adders. Okay, full adder 1, full adder 2, 3 and 4. The question is, if you want to design a this full adder, again one more full adder I am adding to make it as 5 bits. Understood? So based upon the count value, the bit value which is being given, you want to choose the number of full adders. Okay. So normally in a full adder, you know very well, we have 3 number of inputs, A, B, C, and we have 2 number of outputs, sum and carry, right? So check with the first full adder, 3 inputs, A, input B and input C. What are my output? Sum and carry. So same is being followed for all the consecutive full adders, right? So since it is a 4-bit parallel adder, I am choosing 4 full adders. Okay. So now take the example. For example, I want to perform addition for these 2 numbers. 1101 and another one is 0010. Okay. So this is my first input data. Okay. And this is my second input data. So first binary data and second binary data. So all these binary data are 4 bits. See? First bit, second, third and fourth bit. Okay. So I'm going to perform 4-bit binary addition. Okay. Suppose if I want to design a 5-bit parallel adder, I'll be adding one more bit over here. Okay. So let's look into the operation of this 4-bit parallel adder. So I'm choosing this input as A1, A2, A3, A4, the first input data, and the second input data is B1, B2, B3, B4. So what is my first input data which is being provided to the first full adder? A1, B1. What is A1 and B1? Yes, A1 is 1, B1 is 0. So A1 is 1 and B1 is 0. Right. What about my C? Input C? Input C is not given here. So I'm considering input C as 0. So A1 is 1, B1 is 1. C is 0. Yes, sorry. 0 plus 1 plus 0. So 0 plus 1, I'll get answer as 1. 1 plus 0, I'll get the answer as 1. So my sum will be 1. So that sum I have written over here. Okay. So what is my carry? Whether I have obtained any carry? Definitely not. I didn't obtain any carry. So as an input to the second input. Okay. So my input C2 is equal to 0. What about my A2, B2? Yes, A2 is 0, B2 is 1. So A2 is 0 and B2 is 1. Correct. And C is 0. So what is 1 plus 0? 1. Again, what is 1 plus 0? 1. So my sum will be 1, my carry will be 0. So my sum will be 1. Again, my carry will be 0, which will be fed as an input to the third full adder. So same way this process keeps on going, okay, until I perform all the 4-bit addition. So what will be my final answer? I'll get 1, 1, 1, 1. So this is my final output answer. So generally when you perform a binary addition for this also, just perform the binary addition 1101 plus 0010, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 0 is 1, again 1 plus 0 is 1. Yes, same process is being carried out with 4-bit parallel adder, wherein which you can able to perform n number of additions. So I have performed 4 bits of addition at the same particular period of. Okay, so this is how you construct a parallel. Okay, so you in also when you perform a subtraction, we never subtract directly by number. We may take 2's complement of that part. Then we go to the initial. And then we add and then subtract. Sorry, there was an interim and yes. Okay, so normally, even though if it is of subtraction also, we take 2's complement of the sign value and we perform addition. Clear? So now, this is now diagram for a 4-bit parallel subtraction. So I'm using full letter. So here I'm taking an example, 6 minus 4. Normally, when you perform decimal subtraction for 6 minus 4, it is nothing but answer will be 2. So I want to obtain the answer as 2. So let's see how come this 4-bit parallel subtraction has been providing this answer. So now same circuit, like how come you have taken for parallel adder, you are taking the same circuit, but only we are making 2 modifications over here. What are the 2 modifications? Input B, I am using a NOT gate. Okay, NOT gate. Gate means it is used for performing one complement. I told you, if you are performing a subtraction, if you are doing a subtraction, okay, yes, you will be finding out is a sign number. So the sign number you perform 2's complement. So how will you perform 2's complement? First, you perform 1's complement, wherein which all the zeros will be converted to 1 and all the 1 will be converted to 0. And at last, to the least significant bit, to the LSB, you will be adding 1 here, so that you will be obtaining a 2's complement output. So that 2's complement answer again first value. Okay, so first value and you will be getting an answer. So for performing that 1's complement, I am using a NOT gate over here. Second modification what I make here is the input I am adding 1. So previously in parallel adder, I have considered input 0, but here I am considering the input C as 1. Why? Because while I perform 2's complement, after performing 1's complement, what did I do? I add 1 to the LSB. So that adding 1 to the LSB is considered over here, which I am giving as an input over. Okay. 0 will be converted to 1, 1 to 0, and last significant bits, okay, will be added, wherein which 2's complement will be completed and it will be added to the say for example, consider 6 minus 4. So the binary representation for 6 is 0, 1, 1, 0, and for 4 it is 0, 1, 0, 0. What is the 1's complement for 4? Yes, all 0 will be converted to 1, all 1 will be converted to 0. So what will be your answer? 1, 0, 1, 1. Okay, so what will be my 2's complement? I will be adding 1 to the LSB. So when I add 1 to the LSB, so 1 plus 1 is 0, so I will get 1 carry. Again 1 plus 1 is 0, again I will get 1 carry. Again 1 plus 0 is 1 and 1. So I will get this answer, right? So this answer, okay, it is a 2's complement of 4. So now this answer will be added with the first value, 6. So what is my answer? 1, 1, 0, 0 will be added with 0, 1, 1, 0. So when I perform addition, 0 plus 0, 0, 0 plus 1, 1, 1 plus 1, 0, and carry will be 1. Again 1 plus 1 is 0, carry will be 1. In 2's complement, I will neglect what is carry. Carry will be neglected. So my final answer will be 0, 0, 1, 0, which is the binary representation of 2 decimal value. So generally 6 minus 4 is 2. So same procedure will be carried out. Look into the first full ladder. A naught is what? What is A naught? 0. What is B naught? 0. So 0 I have given over here. What is the, when I give it inside an OR gate, 0 will be converted to 1. So 1 and 0. And what about my carry? Yes, carry will be given as 1. Right. So 1 plus 0 plus 0. So the addition will be carried out. So 1 plus 0 plus 1. So I'll be getting the sum value is 0 and carry will be given as an input to the second full adder. So my carry will be 1. And again for A1 and B1, for A1 it is 0 and for B1 it is again 1 will convert to 0. 0 is 1. So 0 plus 1 is 1. My sum will be 1. Whether any carry is generated? No. So carry will be given as 0. So here sum 1, I got 1, 1. The same way each and every process will be carried out. The subsecutive process will be carried out for all the other full adders too. Okay. So in 4-bit parallel circuit, this is the circuit diagram. How you design a 4-bit parallel circuit, okay, with an addition of a NOT gate, an addition of input I'll be assigning as 1, which is nothing but for performing 1's complement, for performing what 2's complement over to the. So start designing a 4-bit parallel subtractor circuit and a 4-bit parallel adder circuit. Okay, so depending upon the number of bits given in your question, you want to either increase your full adder or you want to decrease your decrease your full adder. Okay, yes. So now the next topic is about mux. So how to design and implement a 4x1 mux. Actually, this multiplexer is also the combinational circuit where the output depends upon only the present input value. So whenever you get a question like this, if you want to design and implement a 4x1 mux, the first value represents input, how many number of inputs lines are there, and how second value represents how many number of output lines are there. So 4x1 represents you have 4 number of inputs and a single number of output. So generally multiplexer is nothing but many to one. Okay, you have n number of inputs, but obviously you have a single output line. So you want to design a 4x1 multiplexer. So 4 inputs. Okay, as I told you, 1, I2 and I3. Output I have only single output. Okay, so in addition to the input line, selector lines. This selection input we call it. So selection input is nothing but, see, for example, if I want to get 4 input, okay, 4 input, that is 2 to the power of n. When n is equal to 2 only, I'll be getting what? 4 output or 4 input combination, right? So when I'll get it to be 4, when n is equal to 2. So that 2 is considered to be the selection input lines, okay, which I'm considering as 0 and 1. Selection input S0 and S1. So if my selection input lines are 2, okay, n is equal to 2, my combination will be 0, 0, 0, 1, 1, 0, 1, 1, and my output will be what? For this concerned input, I'll be getting my output. Okay, so always have in your mind for 4x1 multiplexer based upon the question which is being given. So 4x1 in the sense I have 4 input, I have 1 output. Always in a multiplexer, in addition to the input line and outline, we also make use of selection lines also. So how we are going to design, the logic diagram based upon this truth table. So you'll be getting first, how come you are going to draw the logic diagram is first plot this S0 and S1. So S0 is nothing but 1, S1 is nothing but 1. To make it 0, I'm using a NOT gate so that 1 will be converted to 0. So first draw the selection input line with a NOT gate. Then what are my inputs? I have 4 input lines. So I0, I1, I2, I3. Okay. Check with the previous truth table. S0 is 0, S1 is 0. So from where I'll take the line? S0 is 0 means what? Initially S0 and S1 are 1, 1. So when input 1 is given to NOT gate, I will get output as 0. So now for what combination I want to design my circuit? Yes, when S0 is 0 and S1 is 0. So I'll take line from S0 is 0 and I'll take the line from S1 is equal to 0, and then I0 is provided with some input value and giving it inside an AND gate, and then data will be, yes, the output data will be given for an OR gate, so that finally I'll be getting what? A single output, that is 4x1. That means 4 input is being converted into a single output. Same way the second input, second AND gate, third AND gate, fourth AND gate is being designed from 0, 1, 1, 0 and 1 operation. Design a 4x1 multiplexer. So 4 inputs. For 4 inputs I am generating a single output. If suppose if I want to design an 8x1 multiplexer. So 8x1 multiplexer in the sense, yes, I get what? 8 input lines. So 8 input lines in the sense, how many number of selection input lines will be? Yes, n is equal to 3. So when n is equal to 3, so 2 to the power of 3 is 8, right? So I'll get S0, S1, S2, one more selection input line, and then n number of, so four more number of AND gate I will be obtaining, and then the data will be, the output of these AND gate will be given as an input to the OR gate, where I can able to convert all the 8 number of input to a single output. So multiplexer, in the sense, have in your mind always multiplexer has more number of inputs, n number of inputs, but output will be only one output. Okay, so this is what I was explaining you in 8 plus 1 marks, which is 8 inputs and 3 selection inputs, okay, with a single output. Okay, so this is also the logic diagram which I have told you with 3 selection inputs we are plotting. So with 8 number of AND gate, all the output of the NAND gate is again fed and given inside a gate. Okay, so based upon the question, you want to design the okay, yes. So now let's start with the next question, which is design and how to design and implement a 8x3 encoder circuit. So here, same model, encoder is also somewhat similar to multiplexer, but multiplexer definitely you will get output to be one. Only one output line will be available. But whereas for this encoder, you have less number of outputs. Say for example, if you have input line to be 8, a maximum number of input line to be 8, but output will be less number. Okay, the output lines will be less number. Okay, it is not one, it is less number. So here also you want to design an 8x3 encoder. So 8 is represented for input and 3 is represented for output. So this is the block diagram which defines your 8x3 encoder. So I am defining it as Y0, Y1, Y2, Y3. Any representation you can give. Even you can give it as I0, I1, I2, or I1, I2, I3 till I8 also you can give. Okay. So representation is your wish, but you have to give 8 input lines and output line is 3 output lines. So here I am naming the output line as A0, A1, A2. Okay. So this is the block diagram. So once the input and output line has been identified, now you can able to draw the truth table. So your truth table for your input line and for your output line. So in encoder, you have to keep a concept in mind, which means always in an encoder, even though you have n number of input lines, only a single input line will be active for a particular period of time. Okay, for a particular period of time, only one input will be active. All the remaining lines will be in inactive state. Active means on condition, inactive state means off condition. Okay. See for example, so since we have a 3 output, the combination I am choosing here is 0, 0, 0 till 1, 1, 1. So first I am making the first input Y0 to be active. So active I am marking it as 1. All inactive state I am marking it as 0. So when output A0, A1, A2 is 0, 0, 0, my Y0 will be 1, remaining everything will be 0. What about the second case? When the condition 0, 0, 1, my Y1 will be 1, all the other inputs will be off. Okay, so have in your mind always in encoder, even though you have multiple number of input lines, only one input line will be in on condition. So same thing is considered for the last combination 1, 1, 1 also. So after you design the truth table, now you want to find out the Boolean expression. How do you design the Boolean expression? Based on the output value. So for A2, you check how many number of ones are available, 4 number of ones are available. Check it over here. So when this one has been available, when Y4 is active, and when Y5 is active, and when Y6 is active, and when Y7 is active. So what will be my answer? A2 is equal to, you add it together, Y7 plus Y6 plus Y5 plus Y4. Same way for A1 and A0 also. So once I obtain my Boolean expression, I want to draw the logic diagram. So for drawing the logic diagram, first draw the input line starting from Y0 to Y7. Once it has been drawn, now I want to draw the logic diagram for this. That is, once the input line has been drawn, yes, you want to choose Y7, Y6, Y5, Y4. So Y7, Y6, Y5, Y4. I'm giving inside an OR gate because all the variable are, yes, added together. So I am adding it. So for that, I'm using OR gate and my output generated will be A2. Same way, the process is carried for A1 and A0. This is how I design an encoder. So always have in your mind, encoder also we have more number of inputs, but we have less number of outputs. But that too, you have to keep a condition in mind. Always a single variable will be, a single input variable will be in active condition, remaining all the input lines will be on the number which is being given in the question you want to design. So here it is being given as 8x3. Sometimes if it is given as 4x2, accordingly you have to design your input table, you want to design your output variable. Okay, so here for encoder we never make use of any selection input lines. multiplexer only, you'll be making use of one more additional input called as selection input. Okay. And the last problem which comes under this unit 2 is how to design a BCD to 7-segment display. Okay. So this is one of the frequently asked important question, which is how to design a BCD to 7-segment display. So 7-segment display, you are aware about it. Normally, you can able to find its application in your digital watches, digital clocks, in speedometer, in your calculator, everywhere you can able to find this 7-segment display, right? So this 7-segment display, it has been defined with, I'm naming it as segment A, segment B, C, D, E, F, and G. Okay. So now, over with the help of the 7 segments, we can able to display the numerical numbers starting from 0 till 9, right? So how come we can able to display it as such like this? So look into this slide. So 0 in the sense, all the 6 segments will be glowing starting from A to F except G. So G will be in off, remaining all segment will be in on condition. If you want to represent, if you want to display the number 1, B and C will be on, the rest will be off. What about 2? A, B, and G, E, and D will be in on condition, the rest will be in off condition. So same way you can able to display the number starting from 0 to 9. Okay. So for this display, you are going to design a truth table. How we will design that? So starting from the decimal digit 0 to 9. Now E, F, G. 0 I am representing. So 0. Check for 0 in the previous slide. So G only is in off. All the other segments are in on condition. So alone G I will mark it as 0. Remaining segments I will mark it as 1. So remaining all segments I will mark it as 1 except G as 0. What about 1? If you want to get the digital display as 1, the segment B and C will be in on, the rest will be in off. So B and C alone will be in on. On means 1, remaining will be off. The same procedure has been carried out until 9. Okay, why until 9? Because you can able to display is the number starting from 0 to 9, right? So what you're going to do is starting from 10 to 15, I'll make all the remaining digital display to be, that is the decimal digit to be don't care condition. Don't care condition means we are not making use of here. Either the value can be 0 or else it can be of 1. So only for 0 to 9 I am considering over here. So the rest are considered to be don't care condition. So once I have designed my truth table, what will be my next step? I want to design the K-map. So first I have to design the K-map for A, and then for B, C, D, E, F, and G. K-map for. So here in this truth table, I have defined this binary, this decimal digit 0, 1, 2 in terms of binary representation 0, 0, 0, 0, 0, 0, 1. Okay. So now K-map. So K-map, how come you will be defining the K-map? Yes. So first this is the K-map for A. Okay, so how will you define the K-map? So check for the number of ones available. So number of ones available, check it and plot the concerned combination. For the concerned combination, plot the value as 1. So, and the remaining value, I'll be marking it as don't care. Don't care in the sense, till 9, I'll be plotting it as 1. Then from 10, 11, 12, 13, 14, and 15. For 6 values, I'll plot it as don't care. When you check it, you can able to find it over here. For 6 values, I plot it as don't care. Remaining 1, I'll be plotting it and I'll be checking for grouping. So grouping, how come you'll be doing maximum number of grouping? Check for octet. So octet, quad, pair, and isolated. So octet. So octet, while you check for octet type of pairing, check for maximum number of ones first. If maximum number of ones is not available, then check for maximum number of ones with maximum number of don't care. So for that, if you can able to perform an octet grouping, you can able to perform a grouping over here. So this is one of the octet, and this is the second octet, and this one quad, and this is all the second quad. All the corners is being grouped, so that all the number of ones is being grouped together. See to that none of the number of ones is left free. Okay, so same procedure is being carried over for B, segment C, D, E, F, and G. So once everything is being plotted, you start grouping. Once grouping is being done, you will be finding a Boolean expression. For this Boolean expression, now we want to draw the logic diagram. Okay, so how do you draw this logic diagram? Okay, so how many inputs we have? A, B, C, D. So for this 4 input, I will be plotting A, B, C, D, and this NOT gate gives you 0 representation. If A equal to 1, your A bar will be 0. Okay, and for that, you will be plotting the value. So for A is equal to, so check with the first one. A plus C plus BD plus D bar D. Okay, so first, yeah, and I'll be giving it inside an AND gate, and same way I'll take the E, I'll give it inside an AND gate, okay, and then A and C I'll take directly, and all the output from 4 I'll be giving it inside an OR gate, so that my output will be segment E. So A is equal to that concerned value. So 2 AND gate I'm using, and then the concerned input variable I'm taking it directly, that is uncomplemented form, and then the output of these each AND gate is being given as an input to the OR gate. So my answer will be for, this will be for segment A, segment B, segment C, segment D, E, F, and G. So this is how you draw the logic diagram for an BCD to 7 segment display. Okay, so hope you have understood all the topics. So these are the topics which I have discussed as the major important repeat